t, magnitude of r prime, and that's going to be square root of 1 plus squared plus 1, so minus tangent t squared, and that is secant t. Vector t, unit vector t, tangent t, right, is just cosine comma negative sine t. Nice. It will eventually show up over there. Now we need its derivative. So t prime of t. T prime of t is just going to be negative sine t, negative cosine t. And then we need its magnitude, which is just 1. Perfect. So now, by the formula over here, we just, for the normal vector, it's a t prime divided by t. Wow, this is so short. This is really a non-representative problem of this. So negative sine t, negative cosine t divided by 1. And the normal vector t is negative sine t, negative cosine t. And that's the answer. Now, yeah, I know you can't see any of this, but you can just imagine it if you really think about it. Good effort. So let's see if we can. Well, first off, the stream shows that it's alive now. I don't know. Not a representative problem because it worked out somehow in 8 lines. Generally, this is 8 pages long, but we have vector r. Then we find the r prime, and that's simplified nicely into 1 negative tangent t. Then we have the magnitude of r prime, which worked out to be secant t. Then r prime divided by its magnitude is unit vector t, tangent, right? And that worked out to be cosine t and negative sine t when you work out your trig. And then, since vector t is cosine negative sine, then the t prime, which is the derivative of each one of those, is negative sine, negative cosine. And then the t prime is equal to 1. And now when you divide t by t prime, you get the vector, normal vector n. So that is the answer.
Can you scroll up for a second?
Scroll up for a second. I did 100% of what you asked. Scrolling up for a second. If you need more than 1 second, let me know. All right. This is really not a representative example of the whole thing. It bothers me, actually. But such is life. I got lucky on this one. And I picked the one vector that was all the way in the back. Anyway, problem. What's the relationship between the normal vector and the tangent vector? They're orthogonal. Great. Now, what mathematical concept do we know to figure out if 2 vectors are orthogonal or dot product? So, here in blood, theorem, the tangent vector t hat dotted with a normal vector n hat has to be 0. Yes, so we are going to now have a curve over here, and at this point P, we're going to have our unit tangent vector, and then unit normal vector is going to point inwards. So the line that we have here is going to sit in some 3D realm, right? X, Y, and Z. That line is described by vector R of t, which is the set of parametric equations, 2 for 2D, 3 for 3D, and 7 for 7D, whatever. And now when you have, actually it's better if I draw this towards the point over here. So there you go. So this is point P they're talking about. So now I have the line represented by this vector R, which is the parametric vector valued function, right? Parametric equations. And then at the point P, the tangential vector will show. Guys, please remember, I'm actually going to put the old one back. This is like, let's say t equals to t0. Point P is t equals to t1, and so on. So the time is passing. You can see that there is a progression from t0 in time to t1 to t2 to t3 and so on. So whatever amount of time passes from you to get from point, I don't know, Q to point P and so on. The motion on this graph is to the right. So you see that the tangent vector is pointing to the right, and the normal vector is pointing inward, because that big circle we talked about would be filling in on that side, so it's pointing towards its radius.
How come the circle isn't like underneath the curve? Yeah.
No, because it has to match the curvature. You see over here, it has to go along the line for some time and then make a circle. Now, if you change the point, you go to this point here, then this point here will have the curvature go that way. So now, because the curvature goes that way, your tangent vector still pushes forward, and the normal vector is now this way, because the curvature gets you the circle on the other side. So for each point independently, you have a circle to be inside or outside, depending which way it curves. So these are, and since these two guys are always 90 degrees to each other, right, then the dot product between them is 0 at all times. And the normal vector always points inwards toward which the curve is turning, and the tangent vector propels forward. So yeah, that's that.
So
Now they're also
put 0 because when you're finding the vector,
for the straight line, curvature is 0. For the straight lines, yes. But for the lines that have curves, the normal vector, the tangent vector, the curvature is not 0. Now the dot product between two orthogonal vectors is always 0. That's in 11.3.
because you have a sign there, right? In the equation, the dot product of something is the magnitude of u times magnitude of v times sine of theta.
Cosine. That's right. Yes, and the cosine of 90 is 0. Yep, and that kills it. Good. There's also a part on talking about components of the acceleration in terms of normal and tangential acceleration. It's getting a little bit more specific for physics. If you're interested in that stuff, take a look. I won't bother you with that if you are not interested. If you're interested, please, by all means, talk to me. I'll give you a whole bunch of problems to practice. Page 851 in our textbook is very helpful because it contains all of the formulas in one spot. It shows your position vector, which is your vector valued function r, which is a set of parametric equations. Then you have your velocity, your acceleration, which are the derivatives, each one of those components separately. Unit tangent vector is r prime, which is velocity divided by its magnitude, which is speed. So unit tangent vector is velocity divided by speed. Principal unit normal vector, curvature, and then if you're interested in more of these physics formulas, you have them there to further your knowledge in application. 851. And that ends chapter 11.